Alright? Determine the expression for the sample signal. XST in terms of t, right? In terms of t. Right? Sample up. So it's xt multiplied by Coulomb function at 20 Hertz. So the sampling interval is 1/20. 2 marks. See how generous we are with marks. Okay, so this is B1. Any question? Okay, let's go to B2. Determine the expression for the Fourier transform XF of this. So I'm going to find XF. So XSF will be XF. Multiply becomes convolve here. 20 summation K delta F minus K20. Right? This guy is that whole thing here. Substitute inside. Okay? Alright? But what it actually means is that when you convolve, this becomes what? Right? Yeah? So now you substitute. Wherever you see F, you replace F minus K20. I can take out the 5. No? Take out the 5, it's become 100. Huh? So I have cos pi over 4 into where I see F, I replace by this. F minus K20 minus 10 rect F minus K20 minus 10 over 4, that's the first part, plus cos pi over 4 F minus K20 plus 10 rect F minus K20 plus 10 over 4. Okay, where's part B? Part 2. That's it. Questions?
For the Coulomb function, the K20, right? The number after K should be always.
No, this is the sampling interval. K times Ts.
Yes. So this one, when we have to put in period, when do we need to put in frequency?
No, this is in time.
Oh. Oh yeah.
Yeah, this is in time. Yes, this is the sampling Coulomb function, and each of the impulses are 1/20th of a second apart.
The previous question was given in
Yeah,
seconds, so we just put in 10.
Yeah, previously the other question was a periodic signal. This is not periodic. This is a sample signal.
Okay. But for that one, like when we do the convolution frequency,
That's because I'm creating a periodic signal.
So
I'm
we have
not
to
creating a periodic signal here. I'm sampling the signal. When you sample, you multiply with the Coulomb function. When you create a periodic signal, you take the generating function, that means the original pulse, and you're repeating that pulse at the period, capital T. Alright? I will summarize this for you. I'll write it down again afterwards. Alright?
So that's why we, for the last question, we do 1/10 for the frequency though.
Because just now is a different thing. Just now you had a period of 10 seconds. So it was in the time domain is delta t minus k10.
Yeah. So 10.
And then you do the Fourier transform of this, you will get this.
Yeah.
Okay? Alright?
这个断算就背下来以后呢，遇到说
Another question? Alright. So part B, I found already. Last part. Can xt be recovered from the sample signal xs? And if so, explain how this can be done. So what do you do in sampling? So in sampling, what we do is that we take this guy, and we repeat this at the sampling frequency, which is what is happening here. We take xf, which is this guy, this is xf, and we repeat at the sampling frequency, which is 20 Hertz. So I take this, I repeat at 20 Hertz, 40 Hertz, 60 Hertz, 80 Hertz. Now if I repeat it, what will happen? If I move 20 Hertz to the right, what will happen is that if I move this to the right by 20 Hertz, this guy over here will come here, right? This guy at 10 will go to 30, right? Okay, and if you keep doing that, what will happen? All the humps at 10, 20, 10, right now is 0, center at 0, center at 20, center at 40, and so on. All will be double up because they overlap. Correct? They will overlap. Take it down already, right?
Mm. 这样的不是你20除跟 C 在一起不会达到。他讲的是在这里上，在中间写了一个10的话就写了。
它加20的话，这个如果是20的话，这就是那个等于10的话，它这个本来是
它就一出来就是这样的，出来一半一半。
两个 overlap 它们会公式。对。因为就是 period 嘛，因为它是 T 是。
对，看一下看一下。
Okay, I'm going to move this red guy 20 Hertz to the right. Okay? I'm move it 20 Hertz to the right. If I move it 20 Hertz to the right, this guy will come here. This guy will come here. To the right. Correct? If I move it to the left 20 Hertz, this guy will come here. And this guy will come here. You see what I mean by overlap? So in the end, you will have a spectrum with all these humps at all these locations, but it's double the height. Correct? So if I have a band pass filter, I will get back my original now. Agree? Although louder because increased by double. Okay? So yes, the answer is yes, I can recover it using a bandpass filter centered at 10 Hertz and a bandwidth of 4 Hertz. Okay? 4 Hertz because it's between 8 to 12. That's 4 Hertz. I better. So do they have the wireless? Get dangerous. Wow.
刚刚你们直接。
You follow me? Huh? Alright.
What wasn't the wire in the...
No, it was a wire. Because the wire is too short. When LT7 I was using the wireless one, you remember? Hello?
Oh.
It's too loud.
我录了，上传直接回去。
Okay? Okay? Okay. Alright? So this is 4 Hertz. Between 8 to 12. Okay? I don't know how to turn now. Is that
recover?
Never.
And how do you recover again?
A bandpass filter, the blue guy here,
A band
centered at 10 hertz.
band pass
Yeah.
centered at 10 hertz.
Lower cutoff frequency at 8, upper cutoff frequency at 12.
You don't need a stop pass for the metal.
No. Bandpass. So this is 8 and this is 12. Okay? Can?
How to design the bandpass?
I just told you earlier 1 hour ago.
Another module, bro.
Right?
But then we're recovering the double the signal. So
It's okay, that is not distortion. Okay? I speak softly, I speak louder, it's still me. Right? So, change in amplitude equally across all frequencies is not a distortion.
Oh, okay.
So, that's it, one page. And this explain the bandpass.
So, if one, sorry. If one of the hum right is doubled, but the other one is not.
Both.
I mean, for this case, it's both. But for like other questions, like one of the part is doubled, or one of the part is
Have we ever seen that happen?
no. I just asking. Okay.
Okay, let's move on to number 3.
有没有可能？
嗯
有没有可能这样说？这有一个。
我估计还是可以。
你在讲的前面